This is TWiT.
The Zero Patch guys, who I think have found themselves a niche in the world, have produced a Micropatch. Recall that we recently discussed a worrisome local privilege escalation vulnerability in the Windows user profile surface, which affected, or I should say unfortunately affects, all versions of Windows. This was that one that Abdulhamid Nasiri discovered and privately, responsibly, properly disclosed to Microsoft months ago. They then listed this as patched and fixed in August. But after he reverse engineered the change that Microsoft made to see what it was, he was kind of curious. Oh, cool. How'd they fix this? He discovered that the only thing fixed was that the simple proof of concept demo he'd provided to demonstrate the more severe underlying problem no longer worked. The underlying problem remained. So it wasn't fixed in August when it was supposed to be, nor in September or October or last Tuesday in November. On the one hand, if it's exploited, it allows an attacker to elevate themselves to full system, root privilege under Windows. But on the other hand, any such attacker would need to have knowledge of some second credential that would work on the same machine. The cert CC guy, whose name escapes me, I talked about him before. He commented that would, and he correctly said, Will Dorman, that's his name. He correctly said that that meant this wouldn't be as widespread as many other things. Nasiri reminds us that any domain credential would be sufficient. So that does somewhat lower the bar for an attacker. I won't comment on the fact that when Bleeping Computer asked Microsoft about this still unresolved problem, Bleeping Computer were told that, quote, "We're aware of the issue and will take appropriate action to keep customers protected." Of course, okay, I said I wouldn't comment. But what I will comment on is that last Thursday, after seeing that Microsoft still hadn't fixed this for the fourth month in a row, the guys over at Zero Patch created one of their very cool little micropatches that, believe it or not, actually works and solves the problem. It can be applied to any Windows system needing interim protection until Windows gets it fixed. And of course, potentially on older systems that Windows will no longer fix. That's really sort of the niche that the Zero Patch guys have found is, you have to subscribe. You can sign up for free and get this for free, and it will be available until Microsoft fixes it for free. But you can also, if you're wanting to keep older systems alive for some reason that Microsoft isn't fixing, these guys are still fixing all these things. So you can subscribe, and the Micropatch system automatically updates itself, and the patches are, wow, Leo, 23 bytes. So yeah. Anyway, they're available for 32 and 64-bit versions on any Windows 10 system with at least the October or the November updates in place. So again, let's hope that Microsoft gets this fixed in December. It'll be a nice Christmas present for Windows users. Until they do, this little Micropatch is free. You do have to register, however. And I haven't taken any time to research in detail what it was that Nasiri found and what's going on. But the founder of Zero Patch did say that while this issue could, in theory, also impact earlier Windows versions, he said, quote, "The vulnerable code is different there, making the window for winning the race condition extremely narrow and probably unexploitable." Well, that's interesting, a race condition. We've, on this podcast, never had the occasion to discuss race conditions. But it's a common problem that can crop up anytime multiple things might be happening at once where the precise sequence of them happening is important. A few weeks ago, I mentioned the counter timer in the original PC, which used what was known as a ripple counter. A ripple counter in digital logic is a series of individual toggling flip-flops connected in a chain. When a single toggling flip-flop's input goes to logic 1, nothing happens, except it registers it internally. But when that input drops back to logic 0, the flip-flop flips to its other on or off state, whichever the other one is. And if the output of that flip-flop is connected to the input of a next flip-flop, you start to obtain a binary counter, where the number of bits in the counter is the number of flip-flops in the chain. And I should confess, this is how I spent my youth, was like, drawing these things and drawing logic diagrams. And if anyone wants an interesting challenge, implement a toggling flip-flop with mechanical relays. Even if you don't actually build it, just draw them, because I did, and it's an interesting challenge. Anyway, the problem is flip-flops in the real world do not toggle instantly. They have what's known as a propagation delay, which means that their output changes just a little bit after their input goes to 0. The flip-flop's internal logic takes a bit of time to sort things out. This means that when the input at the front of this ripple counter goes from 1 to 0, which will start to update to the next count, the changes in the count might ripple down through the length of the counter. Okay, now let's say that you want to take a snapshot of the counter's current count, but you have no idea when that counter might be counting. This is where we get into a perfect example of a race condition. If we happen to take a snapshot of this binary ripple counter while that new count is rippling down the length of the counter due to the propagation delay in each of the counter's stages from one stage to the next, we'll obtain an erroneous reading due to a race condition which we've created between the counting event and our sampling of that counter. And, race conditions aren't just electronic. They can occur socially, too. They're a favorite vehicle of screenwriters who have one person racing to answer the phone before someone else gets the chance to do so to avoid some embarrassing outcome. A race condition in real life. In electronics and in software, these race conditions can be quite tricky to spot, and they've been known to introduce some of the hardest to find bugs there are. The reason may be that they may not occur predictably or even often, but just maddeningly. For example, the state of that ripple counter might be properly sampled thousands or hundreds of thousands of times before the sampling just happens to catch the counter in the process of rippling. The other maddening thing is that the act of observing the system might change it. For example, adding the tiny capacitance of a high-impedance oscilloscope probe when checking a high-frequency signal can change its timing just enough to prevent the problem from occurring while you're looking at it. And the same goes for debugging code. If you step through the troublesome area of some time-sensitive code, everything works while you're watching it. In fact, the problem only occurs, for example, on odd Tuesdays when the moon is full and the mailman is late. Otherwise, everything works fine. So our lesson here is the need, I guess first the appreciation of, or appreciation for, and then the need for true vigilance in any asynchronous multi-threaded application where more than one thread might share access to variables or objects, always consider every implication of that very carefully. Always keep the possibility of these sorts of collisions front of mind, and work very hard to never create such problems in the first place, because it's far better to prevent them than to have to go back and try to find those gremlins later. And as I was thinking about this, about the nature of the need to appreciate how big a problem this is, I sort of got into thinking about new coders who, anyone starting out at the beginning is going to begin their craft without any appreciation, because you can't have any in the beginning, for the subtleties and nuances of the way complex coding problems are best solved. And the word best is critical here. For newbies, it might at first seem that any solution to a problem with computers is as good as any other. After all, they're all solutions, aren't they? But with time and patience and lots of practice at coding, a coder gradually matures to learn that there are superior, more elegant, and more robust ways to think about, to frame, and then to solve a problem that may have many solutions. Most coding problems do have many solutions. Yet it's often the case that there really is one best way. And I think that the great joy of coding comes from the satisfaction of knowing that you have found the best solution. I'll often code something, and then I'll wonder, having done so, I'm done, if I can't find a better solution. What I think happens is that the act of solving the problem the first time teaches us something about the problem that hadn't been initially appreciated. For example, I might have needed to add an awkward bit of code at the end to handle an edge case that I hadn't seen coming. But if I'd appreciated it at the start, as I do now at the end, might I have come up with an overall superior solution that inherently incorporated and didn't need that special case handling because it solved the problem the right way. So the point is, I may have just learned something about the problem that might now suggest an entirely different and superior approach. So what I often do is I'll leave what I wrote in place so I can go back to it if my intuition is wrong and I don't find a better way. I'll open up a big region of blank space in my editor and immediately tackle the same problem again, but this time starting with a deeper understanding of the problem I'm trying to solve. And for me, that's the continual fascination that I have with coding. It's why I enjoy it so much. Is 50 years later, 50 years after having started this, I'm still learning things. I'm tackling new problems. I'm taking all of this experience that I have, but I'm finding that I can still recast a first solution in something better the second time. And it's true, it will make no difference in what that chunk of code does, but it might make a difference in the way it does it. One solution may be aesthetically cleaner and superior to the other. And as utterly abstract as code can be, within its own little microcosm, it really is possible to create little works of art, little constructed gems. And I know that not everyone obtains fulfillment from building things. And not everyone is as curious as I am. And not everyone may have the luxury of taking the time to find that one best solution. If you are those things, then what I've just articulated makes all the sense to you in the world. And if you aren't those things, maybe you can now understand a little bit better those of us who are so weird in this particular way. And Leo, I have a feeling you may be one of them.
I'm in that former group, you bet. It's one of the things I go home and can't wait to get going on. Yeah.
Yeah, there just is something magical about it.
Race conditions are a big problem these days because we do concurrent programming so much. So, we have multiple processors. So it's not at all unusual to have multiple processes running at the same time. I have to say, though, I think some of it is because we made a big mistake many years ago going with imperative programming and programming with side effects. If you don't have side effects, you don't have problems with concurrency. You don't have dependencies. I guess sometimes you need side effects. For sure you do with I/O and so forth. But it seems to me that some of this comes from just a mistake made early on in how we write code. That's why I'm a fan of functional programming.
I think that's probably true. As you were suggesting that it was fundamental, I was thinking of, for example, I have some code which is manipulating a list, and where I'm inserting an object into a list of objects. So I'm in the process of taking the pointer that points to the next one out and replacing it with a pointer that points to the new one, and then putting the pointer that was pointing to the last one at the end of the new one, inserting that into the list. Well, that's a fragile moment in time.
Exactly, right. And if another process is counting on that list, it's in an unknown state.
Yes. So if something else, another thread in the same process, or if it's a cross-process object which is available, it might go and take, it might get swapped in, time sliced in, and be attempting to traverse that list while I'm in the process in a different thread of maintaining it.
Exactly.
And that's where that's another good example of something that might work for 3 years and then just blow up. And it's like, what happened? And again, it's like just a moment in time where that race condition between two threads trying to simultaneous access. And so there are solutions in Windows. It's called a critical section. You're able to request a critical section of code that no two threads are allowed to be in at the same time. And so in my own list management code, I grab a critical section, do the work, and then I exit the critical section.
You lock it in effect,
It's basically lock that little block of code.
And that's why it's called a race, because the winner of the race can vary, and whoever wins will get a different result. Ideally, with code, you want the same inputs to produce the same outputs every single time.
Determinism.
It's determinist, and the degree that it's not is the degree. There are languages like Erlang that are designed to handle concurrency specifically for this. I think if Windows critical code worked better, we would see less of these bugs. But apparently, either people aren't doing it, or maybe it's sloppy coding. I don't think it's always sloppy coding. I think sometimes it's just you don't really realize the side effects that you're introducing.
Well, to take Microsoft's side for a minute, can you imagine touching the code of Windows?
Right.
I mean,
it should all be critical section. The whole thing. Do not touch.
I mean, I have the advantage of being a one-person team who wrote everything that I'm doing and touching. So, if I make a mistake, it's mine. At the same time, I'm less likely to, because it's mine. Nobody wrote anything that other than I did, and so I'm not looking at code thinking, okay, I think long time ago, you and I talked about some of the fundamental problems of coding. One of them is bad variable names, right? You name something and badly, and then later you think that it's a good name, but if it's a bad name, it doesn't really describe what you think it does. And so that's one of the problems. And the other is fuzzy definitions. If you're not really sure of what some code does, you're in trouble, because the computer's not sure either, and if you're not sure, it's not going to be any more sure. And so there are again, as you spend time coding, you end up sort of with like your group of things that you learn to watch for. And I've learned the importance of being very careful about what I call things, because later I'll come back and I'll think they're exactly what I called them. And if I'm wrong, I get myself in trouble.
Yep. Well, and you also get some sympathy for people who make mistakes, because it's a hard and a high stakes practice. It's not easy.
Which is what makes it fun.
That's what makes it fun. Yeah.